Okay, let's get this started. So, since it's been forever since I saw you, I'm just going to repeat myself just a tad a little bit to make sure that we're all back on the same page. We kind of remember where we left off. Last time I spoke about annual percentage yield. There's something called APR. There is something called APR. The last thing we talked about was called APY, annual percentage yield. It assesses the interest accrued in an account over a year's basis, and it basically seeks to level everybody. So there's all these kinds of ways we can assess interest: compounded continuously, compounded monthly, and semi-annually, and all that kind of stuff. And we realized that last time we saw 9.5% compounded. I believe we did quarterly. It was actually something like 9.84% when we actually looked at the end value compared to the original value. So sometimes the quoted percentage isn't the actual percentage you're getting, and that's kind of weird. So the APY decided to just, no, we're going to level everybody, and we're going to think of all these different ways of assessing interest in terms of simple interest terms. So you know what interest you're getting at the end of the year. And so that guy started out by looking at, well, the interest. This is the interest that you would have gained in 1 year. So that would be the value of your principal and interest. So this is the percentage of original. That gives principal plus interest. And then what we did is we subtract 100% of the original amount. And basically that gives us, if we find the difference between these two, we get the actual percentage that comes from interest itself. And we multiply that by 100%, just write it in nice percentage terms like this, and that's where we sort of ended. So regardless of how your interest is computed, if you hit it with this formula, you'll get the actual interest that you actually earned at the end of the day, regardless of what they told you that you were earning. There is I don't believe I told you about this, there is a compounded continuously version, because it doesn't work with that. And if you know it's compounded continuously, you sort of have to use a different formula for APY, because the interest from the compounded continuously version uses E, so it ends up being E to the R minus 1. So that's where we sort of left off. And as I mentioned, the APY I don't know if you guys actually started noticing, but these are used by different people who want to tell you about different things. So if loaning firms tend to use this, while investing firms tend to use that, because this guy is always going to be slightly bigger. It's going to be equal to if it's simple interest, but it's going to be slightly bigger otherwise. And so if someone wants to borrow money, they're going to tell you this thing because it's going to be smaller. Hey, I'm going to lend you this money at 9.5% interest, but actually it's 9.8 if you did the APY. Or maybe even higher if it's like a credit card, which is compounded daily. And however, an investment firm would tell you, oh, if you invest money with me, the return on your investment is going to be 9.8 APY, but it's really 9.5, which is compound. Okay? But it's just a way to market you and entice you. So these two things are actually different, and you should be aware what each of them means, and be aware that depending on the person who's quoting interest to you, they might quote one versus the other, and you should just know what they each mean. So that's where we kind of left off. Now, I want to actually move on to a completely different section because technically we finished the section here. If you're reading along in your books, 3.1 is where we started. That's the section that dealt with simple interest. 3.2 is where we dealt with compounded and continuously compounded interest. 3.3, which is what I'm going to talk about now, mentions something called the future value of annuities. And the idea of a sinking fund. We're going to talk about what that is and what's an annuity. And 3.4 talks about present value of annuities. And things like amortization. Now, this is what I'm going to do now, and this will be the last topic in the financial math section of our course, so we should be done with financial math mostly by today, but it'll spill over into a little bit of next week, and then we'll move on to something else. But one thing you might have noticed when we were studying these two sections is that we always pretended, oh, we just put money into this account one time and we just watch it. But that doesn't really happen, does it? People repeatedly put money into accounts, right? And that's how an annuity comes in. So now we're going to deal with a scenario where we're not making one-time payments, we're making multiple payments, and how the math actually pans out in that situation. So, how about future value of annuities? Definition, and let me tell you what an annuity is. Does anyone know what an annuity is? Have you heard the phrase before? You've heard about it. You know what it is? It's just a sequence of regular payments, that's it. So yeah, they could call it regular payments, and I'm not making any moral judgments here or anything, but in finance, people always make complicated names for things, and I'm sure no one really understands what they're talking about. Oh, you just do this annuity and you amortize this and you apply for this debenture and blah, 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 blah. So yeah, I guess I need to pay this guy money to manage my money because this is all complicated. No, they just rename everything to make it seem complicated. It's just how it is. So an annuity is just a sequence of payments. That's all it is. You're making regular payments over time. And if all payments are the same and interest is assessed at the end of each pay period, we call it an ordinary annuity. So we're going to look at the situation, and this is what's considered in this class. The other is a little bit more computationally complex. So we're just going to look at, you're always paying in the same amount of money every month or every week or every day over an extended period of time. And we kind of want to examine what's going to happen to the value of such a fund if you keep paying into it, under the assumption that interest hits you at the end of every pay period. So that is just kind of modeling the situation where if you were to put your money now into an investment and it's in the middle of the month, they're not going to give you all the interest for that month. They start counting interest after you invest. So that's the scenario there. And that's what we're going to look at. we're paying money regularly into some account, it's always the same amount of money all the time. And if I deposit money this month, it gets hit with interest the following month, and then the following month, and then the following month. So that's the scenario. And we're going to look at that. So, I want to find a formula for this. So let's set up some variables. Let R be the regular payments. Little r be the APR. N number of times compounded. Yes.
What's the ordinary annuity?
That's an annuity.
Yeah, is there any like?
Oh, that is being defined by this sentence here.
Oh, okay.
So an annuity is just a sequence of payments. If you assume that all payments have equal value,
Oh,
we call it an ordinary annuity. Because you could deposit different amounts of money at different times. But we're pretending you're always depositing the same amount of money over time. And let M be the number of periods. So that's maybe month, maybe the total number, so that's really going to be the N times T, which we've seen before. We're going to use the variable payment just to kind of make writing a little bit easier. I don't know how much easier, but a little bit easier. So when you copy that down, I'm going to need a lot of board space to kind of work this out. So,
Is there a unit for the big R?
no, the big R is a monetary value.
Ah.
So it's going to be like, it's a dollar amount. It's going to be like $1,000 every month or something like that. That would be the big R. Okay, so here's what it will actually look like when this starts panning out. So this is the now, and you're paying money into the future. So this is period 1, which might be a month or a week or whatever. And then that's period 2, period 3, ... all the way up to period M minus 1, all the way up to period M. Okay? And you are making payments this whole time. So you put down R dollars into the account. On period 2 you put R dollars, on period 3 you put R dollars, on period 4, all the way up period, you're putting in R dollars every time. Now, what's going to happen is that at the end of this period, I want to know how much does all this add up to. So, FB, which as you might recall means future value, right? So at the end of this time, how much money I'm going to have into the account. So the money in the account is growing by some interest, but I keep putting money in while it's growing by some interest, and every time I put money in the following month, that money starts growing by interest. How much does this all add up to is what we want to know. So, can anyone guess what this thing that I put in is going to be worth at the end of the day? Take a guess. We're being compounded n times per year. What is this going to be worth at the end of the day? Right, so pretend that's your principal. What would it be worth over here? How would you calculate it? What formula would you use? It has been a long time, hasn't it? You use use the compound interest formula, right? So what is this value? It's going to be r times 1 plus r over n to some power, right? And that power represents the number of times it's hit with interest. Now by our assumption, it gets hit with interest at the end of the next period. So there were m periods, which means this guy, this money that I put in now, he's going to start being hit with interest at this point. So he's going to be hit with interest m minus 1 times. So that's going to be the power. This is how many times we're compounding it. Similarly, this guy is going to be hit with interest m minus 2 times. This guy is going to be hit with interest m minus 3 times, and so on and so forth. And this is going to continue. This guy is going to be hit with interest literally 1 time because he gets hit with interest at the end. This guy doesn't get hit with interest because he would have been hit with interest starting the next time. So that's what the sequence of payments are going to look like. At least that's what they're going to build up to eventually. The very first payment I make gets hit with interest in all future periods. This one gets hit with interest in all future periods, so that's how they all line up. And so now what we want to do is we want to add all these guys together. How are we going to add all those guys together to get a nice formula? Well, we're going to use a little trick. Call this equation 1. What I'm going to do is I'm going to take equation 1 and I'm going to multiply both sides by 1 plus r over n. So that means this is going to become 1 plus r over n to the m plus 1 plus r over n to the n minus 2 plus 1 plus r over n. This is n minus 1 now, and that's n minus 2 plus dot 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 1 plus r over n squared plus this is going to be 1 plus r over n. And so that's equation 2, where I just multiplied equation 1 by 1 plus r over n. And now what I'm going to do is I'm going to do a subtraction. So what I'm going to do is I'm going to take equation 2 and subtract equation 1. Now when I do that, on this side what's going to happen, this is 1 FV plus r over n FV. So the FV minus the FV, I'm just going to be left with r over n FV, right? And then, so I'm taking this line, subtracting that line. So this minus that, this minus that. The next guy here is going to minus that. This is going to minus that. This will subtract the guy just right before this one. And that doesn't get subtracted from anything. So at the end of the day, you realize that only 2 things really survive. There's this guy, minus that guy. And so that's that. And so now basically I just solve for FE. FE equals r is a common term, I can factor that out. It's going to be 1 plus r over n to m minus 1 over r over n. And of course the m is the number of periods, which if they tell you how many times it's being compounded per year and you know how many years there are, that is just going to be given by n times t. So we get the following. So I'm going to do a notation change here, just to be aware that the formula is the same, I'm just changing the notation. Notation change. I'm also going to change the notation for r, because it's typical. So FB would end up being equal to, the R we usually abbreviate it as PMT, which stands for payment. So this R is the same guy as PMT, which is the payments. Because that's usually used. And so we'll have this. And that's the formula. That's how you would add up a bunch of things where each thing is being hit by compound interest starting at a different step in the journey. And that's how much money you would have at the end of this journey. And the journey ends, nothing lasts forever. Yeah.
We're not gonna have to show like how to derive.
No, you just need to know that. Yeah, I just decided to.
Oh, we don't have to do
Is that what you guys were worried about? How am I gonna do? No, come on, this is finite math. I'm not gonna ask you guys to prove stuff. Just know the formula and know when to use the formula.
Yeah, I was like,
I lost it after the first
Yeah, it's
one.
like that's a nice little trick though. Legend has it that Gauss, who was a very famous mathematician, used this trick when he was like 4 years old or something.
Wow.
When his class was being rowdy and the teacher just said, "Everybody sit down and be quiet, add all the numbers from 1 to 1,000. You know, because they were just learning how to add with little pebbles and stuff. And she thought that would keep them all quiet, and Gauss was like 3 minutes later just, "Here's the answer." How did he do that? Well, he did kind of like what we just did. He just had, he wrote this down, he's like, "I'm not writing down 1,000 numbers." But he didn't multiply them by anything. What he saw was, I can just turn them around. And he's like, well, that's what the teacher wants me to have. That's actually the same thing. And notice what happens if I add them together. This is 1,001. That adds up to 1,001. Hey, that also adds up to 1,001. They all add up to 1,001. So you just had 1,000 times 1,001s, and of course he could multiply it when he was 4 years old because it's Gauss. And so he just said, oh, these numbers are going to add up to 1,000 times 1,001 all over 2. And he computed that and gave her the answer. Meanwhile, all the kids in his class were up to 7, 8, 9. Yeah, so that's a very common mathematical trick. When you want to add up a bunch of things, just find a way to copy the list and tweak it in such a way that if you subtract it, you get back the original thing you were looking for. It's a common trick. You don't need to know how to do it, though, but that's what was going on. Everyone was so worried. Oh my God, we're going to have to know how to do this? No, just know the formula. That's it. So let's actually do an example here so you can actually see how it's going to pan out. You deposit $1,000 per month into an account. Compounded monthly at, let's say, 4% APR. How much money would you have after, say, 40 years? Question. So, as you can see, this is different from the problems we were doing forever ago. So it's not like you're making just a one-time payment and just watching it for 40 years. You're continually making payments every month for 40 years. Let's suppose you were that consistent. Okay? and you're hitting a 4% interest rate over that time. How much would you have at the end of this period? Well, the future value of this money is what I want. I don't actually know that. But what I do know is that I'm putting in payments of $1,000. I also know that the interest rate is 0.04. I also know that the N is 12, it's compounded monthly. I also know that the T is 40. And that's all I need for the formula, so now I'm just going to plug it in. So your FV is going to be equal to the payment, 1,000, times 1 plus 0.04 over 12, raised to the 12 times 40 minus 1 over 0.04 over 12. Make sure you can plug that into your calculators and tell me what numbers you get after doing that. So definitely try to plug it in. Because on the test you tell them, I don't know how to use my calculator. I can't help you. So make sure you know how to use it before the test comes up. And remember, PEMDAS parentheses are important where they go. If you have a calculator that you can actually see on the screen what you're typing as you're typing, you should notice that you would need parentheses around this part. You would also need parentheses around this part. You're typing it out all at once. If you're not, I would build up to it. So I would take 0.04 divided by 12, add 1, get the result, power, parentheses, 12 times 40, close parentheses, enter, get the result, subtract 1, get the result, times 1,000, get the result, division sign, parentheses, 0.04, division sign, 12, close parentheses, enter. So that's how you do it piece by piece. You have to follow PEMDAS. Anyone got it? What number are we getting? Did you get a number?
Yeah.
What did you get?
1 million.
1 million.
Yeah, what are we rounding?
1 million.
$181,961.34. I did it twice, so it should be right.
That's how much you would make.
Yeah, I didn't want to say
Over
it
40.
because I was like 1 million seems
It's like, no, that sounds like a
I
lot,
don't want
right?
to be wrong.
That's the magic of compound interest running for 40 years. And you're like, I've been saving for 40 years, I better be a millionaire. You would be a millionaire. Now, the reason why I chose these numbers for this example is because to some extent they are realistic in the sense that the total stock market returns around 4%. Like after taxes and all that stuff. And of course, everyone's personal situation would be different, but on average, you're going to make 4% in the stock market over a long time. As long as you don't actually look in your account at the point of a recession. You're pretty much averaging that. So, if you start at 20 years old, putting away $1,000 a month, when you retire at 60, you're a millionaire. This is the get rich slowly scheme. Right? Hey, dude, you want to get rich slowly? Yeah. This is how you do it, compound interest. Now, there are ways to speed up this process. A lot of people have done it. All those people on YouTube, you see like, I retired at 35. Yeah, they actually use this to their advantage because it's amazing. You'll think, but I'm only putting in $1,000. Yeah, it adds up to that much under compound interest.
So you have to deposit 1,000 a month?
So if you can actually keep that up for 40 years, so you can just decide what you want to do. You know what, I'm going to take risks, I'm going to get my own business. Whatever you're doing, just make sure you can manage to tuck away $1,000, right? take whatever risks you want, get divorces, travel the world, whatever. If at the end of your life things just didn't work out, at least I'm a millionaire. You know, you can get to have your fun, have your cake and eat it too. And compound interest is how you can do it. So, and by the way, it's even a little bit more amazing. Let me ask you this. Did you actually save $1 million over 40 years? How much did you actually save? How much of this is interest?
Oh, wow.
How much was your actual money? Yeah.
480,000.
Yeah.
How did you get that? Explain how you got it.
12 months for 40 years. It's 480 months, and then 1,000.
Right, so you're going to take the total minus the payments that you made, right? So you had,
I just did the payment.
yeah, so you had 12 times 40 times 1,000, right? So that's the actual money you put in. And what is that?
480.
Only 480,000 of that was your actually hard-earned money. Everything else you earned by not doing anything, just by having it in the account. And the total was 1,181,961.34. So how much of the heavy lifting did the market itself do? Yeah.
$701,691.34.
The market outpaced you. Like you literally got more than the money you saved just in interest. And so this is why Einstein said one of the eighth wonders of one of the wonders of the world is compound interest. It's totally amazing how it kind of works out when you're being hit with interest compounded. You can start out very modestly, and if you look at your account a year from now, 2 years from now, 3 years from now, it's not going to seem like anything is happening. Forget about it and look at it 40 years from now, you're a millionaire. It's like what? It's like magic. But it's not it's math. It actually works out. This is what it adds up to. What?
They're not going to pay you back.
They have to. That's how it works. People do it. Like I'm not. People actually do this. Not everyone is born rich, you know. At any given time, like 80% of the rich people were born poor, and they made themselves rich. This is one of the ways they do it. They take advantage of interest. And so they can do some work, and then the interest on their work actually does more work than they did. And that's how they build wealth over time. Okay. How much time do we have?
10 minutes.
Okay. Now I want to look at sort of the flip side of this. We're not done with this. We're going to be comparing things a little bit, well, next class. On the flip side. Oh, let me tell you about first. And I guess we'll end with this. I'll tell you about a sinking fund. So we just derived. You don't have to remember how to derive it. So this will be the value of an account after a period of time where you're making regular fixed payments over time, compounded n times per year at R% APR. Okay. Now we can actually solve this for this value here for payment, right? So it can essentially multiply by the reciprocal of this fraction here, so multiply by that and then divide by that. And so you have here the future value times R over N over 1 plus R over N NT minus 1. And this guy here is called the the sinking fund payment formula. So this is what a sinking fund is. And a sinking fund, well, what this is an account you make payments into for some future obligations. So mathematically, it's just me moving around some symbols on a page. Interpretively, actually what's going on is now I'm changing the point of view, right? So now let's say I have a goal in the future that I want to meet. Let's say I know, oh, I want to make a certain amount of money 10 years from now. What payments would I have to start making now and regularly so that with compound interest, I'm going to hit that target? This is the formula you would use to do it. So here is where you know the future value, right? Before I knew what payments I was making and I'm going to calculate how much that may be. But let's say I already have a target in mind. At some point in the future I want some amount of money. What are my payments now to achieve that? So and if you open an account for that purpose, it's called a sinking fund account, and it's based on this formula, so it's called the sinking fund formula. So let's say you want to have $150,000, let's say 18 years from now. So maybe you just had a newborn kid and like, man, I gotta get my life together. I'm gonna save up some money to send this kid to college 18 years from now, and I'm hoping that will do it. Like the way that tuition fees are, I don't know. But let's pretend that that's what you did in your mind. You know what? My kid's 18th birthday, I want to give him $150,000 and say, go to college and study, dude. Be better than me. So you have that goal 18 years from now. And let's say you have an account, promises, that's a certain, no, never take promises. To give you, let's say we're being a little bit generous here, 5% APR. Compounded monthly. What should your monthly payments be? So you start with a goal in mind. I want to have $150,000 socked away for 18 years from now. I'm going to open the account and withdraw it, and I better have $150,000 in there. What are the monthly payments I need to be paying now so that in 18 years, that's how much money will be in the account? Well, you use the sinking fund formula, which I just erased. So here, I don't know what payments, but I do know the future value I want. I want $150,000. They're giving me 5% interest rate. It's compounded 12 times per year, and I'm leaving this for 18 years. But I'm not just leaving it, I'm continually paying $1,000. Not $1,000, I don't know how much I'll be paying. That's what I want. But using this formula, my payment is going to be $150,000 times 0.05 over 12 over 1 plus R over N, the NT minus 1. That's roughly what. Now again, if you're typing this all into at one time on your screen, you need parentheses over the entire numerator and over the entire denominator before you put the division sign. And I didn't tell you the numbers here. So this is 0.05 over 12, and this would be 12 times 18. So to have 150,000 18 years from now, what payments do you have to make? Assuming you'll get 5% compounded monthly.
429.55.
What?
429.55
Do we agree?
Yeah.
So for that much a month, you can give your child a college education. Or at least buy 2 textbooks with how things are going. So that's a sinking fund formula. Tomorrow we'll look at the present values of annuities. Well, not tomorrow. Tuesday?
Tuesday.
Alright, we'll stop there. Well, a few more minutes, but now we have time to start anything else.
So we have
I like that.